Hello, and welcome to lesson 26 of this introduction to calculus with Wolfram U. The topic for this lesson is indefinite integrals. So let's begin with a brief overview of the lesson. So in the last lesson, we talked about the fundamental theory of calculus, which connects a differential calculus and integral calculus. So for example, if I said find the integral of this function 4x cubed from 2 to 3, then the answer is simply 3 to the power 4 minus 2 to the power 4. That's 65. And that's because an antiderivative of 4x cubed is x raised to 4. Let's just check that with d. So if we try the same thing with integrate, but now tell it to find the integral of the function from 2 to 3, you get back just the same answer. So what we learned is that the antiderivative is in fact a very nice way to do integration. And hence, we give it a special name. We call it the indefinite integral. So the goal of this lesson is to review the indefinite integrals or antiderivatives that you learned so far. But before going on, just a few notes. So first of all, to repeat myself, the antiderivative will now be referred to as the indefinite integral. And sometimes people just say integral. So if you take integrate and you find the integration of f of x comma x, then the answer is x to the power 4, for example, because it's really computing an indefinite integral when you do not give it any range. Notice one thing, that the answer from integrate does not include the constant of integration, which you would learn in a course on calculus, so you must put this yourself. So please be careful when you work with indefinite integration. You will need to put that constant by hand. Now, if you want to compute a definite integral, then you must actually put in the lower limit and the upper limit, and then you get back the same answer you did early on, which is 65. So here is a plot showing the function and its integral. And once again, please note that we have set the constant for the integral to be 0 essentially. So let's begin now with some examples. So if you take a constant function, then the integral of this function is just k times x, where k is the constant. So again, mentally you must just put in the constant of integration, so you get kx plus c. So for example, if the function is 3, then the integral is 3x. So here is a picture of the function and its integral. And notice that I'm putting the evaluate over here inside the plot, and that's because I'd like integrate to do its work before plot does the plotting. Okay, on to a linear function. So suppose you have kx plus b, then its integral is kx squared over 2 plus bx plus c. That plus c again comes from the constant of integration. So for example, if you have 5x plus 4, then the answer is 5x squared over 2 plus 4x. So you have the plot of both the function and its integral. Okay, on to power functions. So if you have x to the power a, then its integral is x to the power a plus 1 over a plus 1. So that's the answer with the constant of integration. So for example, if I give you x cubed, then the answer is x to the power 4 over 4, which you see in the plot over here. Okay, on to trigonometric functions now. So if you look at the sine function and the cosine function, then the integral of sine is negative cosine, because the derivative of negative cosine is sine. And the integral of cosine is sine. And so we have two important indefinite integrals for sine and for cosine. So here's a plot of the functions and integrals. Okay, so on to slightly harder examples. So if I give you secant times tangent, or negative cosecant times cotangent, then in the first case the integral is secant of x because the derivative of secant of x is secant of x times tangent of x, and similarly for the second example. So we now found two more trig integrals. So here's a plot of all the functions involved over here. And as my final example, let's take even harder trig functions. If it gives a secant x square and negative cosecant x square, then the first integral is tangent of x because the derivative of tangent of x is secant of x the whole square. And similarly, the derivative of cotangent of x is negative cosecant of x the whole square. So again, here's a plot of all the functions and their integrals. Okay, so that's all that there is to today's lesson. It's a short lesson where we talked about the antiderivative of a function and given it a special name, namely the indefinite integral. And what you've learned is that you can find the indefinite integrals of many functions: the constant function, the linear function, the power function, and several trigonometric functions. Now, in most cases, you can simply call the integrate function and it will find the indefinite integral for you, but make sure you put the constant of integration. And that's really the core of indefinite integration. But in the next lesson, we'll talk about the substitution rule, which actually makes things easier when you have more difficult examples and perhaps more interesting examples to talk about. So I'll stop over here. Do review this very important lesson. It's not very difficult, but it's important and basic to everything that follows. And then the next time we'll talk about the substitution rule. So thank you very much. I'll stop over here.